Hello. In this video, we are going to take a look at curve length and surface area of a three-dimensional figure. We're not really going to look at how the formulas are developed. We're just focusing on how to actually use the formulas to find these two things in here. So let's start with curve length. This is the length of a curve, also known as arc length. Has a lot of different names. Here's the formula, though. The requirements for this is that f of x has to be a smooth curve, meaning that its derivative is continuous on our interval from a to b. And then I get this formula here. So looking at the formula, I've got two versions of it. Just depending on which one, everyone's easier to use based on the look of the actual equation. Usually if you have a function that's a little more horizontal, you're going to integrate with respect to x. And if it's something that's more vertical, we'll integrate with respect to y. In both cases, though, we're going to be taking the derivative of the given function, then squaring that, and then adding 1 to it, and then plugging it into that square root. So really the idea behind this usually is to simplify what's in the square root so that either a u substitution works, which doesn't happen very often, or you get something that you can write as something squared so that the square and the square root here will cancel out. Okay, so let's do an example with this. Okay, so we want to find the arc length of the given curve on the interval from 2 to 4. So I've got x equals y to the 5th over 5 plus 1 over 12y cubed. Now it solves for x here, which makes me think I should probably be integrating with respect to y. You can always check the graph if you're not sure, you want to see exactly what it looks like. If I take this one and graph it in Desmos, Desmos is great for graphing things that are solved for x, as opposed to like your graphing calculator, which is going to require that you have it as y equals something in terms of x. But I can see here that this is more of a vertical curve. It's kind of going up and down rather than left to right as I progress through it. So all of this is telling me that I want to integrate with respect to y. So let's set this thing up. So remembering that formula, the first thing I need to do is find the derivative of this. And so I'm doing just straight power rule here for derivatives. Which we spent a lot of time integrating in this class, so be careful to not confuse the two. With the derivative, the exponent comes out front, and then you reduce the exponent by 1. So that 5 goes out front and cancels with the 5 in the denominator, and then you get y to the 4th. And then the same thing with the other term. Remember that 1 over y cubed is the same thing as y to the negative 3rd. So if I take a negative 3 and subtract 1, I'm going to get a negative 4 there. And then the 3 and the 12 will end up reducing, and I get that 1/4. Okay, so next step is to square this and add 1 to it. So it looks something like this to start. And there's a couple of different ways to proceed from here. One is you could distribute out the square here. So you do y to the 4th minus 1 over 4y to the 4th times y to the 4th minus 1 over 4y to the 4th. And that works great. It is going to require you to factor, though, a little bit more difficultly, but it does work out. Another option is to add these two fractions together. So I'm going to rewrite the y to the 4th using a common denominator of 4y to the 4th. And so I'm multiplying top and bottom by 4y to the 4th, and I get 4y to the 8th over 4y to the 4th. And now I have a common denominator, and I can actually subtract these two fractions and turn it into one fraction. Okay, so I get 4y to the 8th minus 1 over 4y to the 4th. And now I'm going to go ahead and square top and bottom of this. And so I get that 16y to the 16th minus 8y to the 8th plus 1. This might be a good time to pause the video and kind of work that out yourself to make sure you get the same thing. Don't forget to square the denominator. And then I know in the next step I want to add this to the 1 out front. So I rewrote the 1 using that common denominator of 16y to the 8th. So now I can add these two fractions together, and there's some like terms there that I'm going to be able to combine. I've got the 16y to the 8th and the minus 8y to the 8th, which will combine to plus 8y to the 8th. So I get this nice little rational expression here. And remember, I have to plug this into a square root. So ideally, these are two things that are perfect squares. So the square and the square root will cancel. So I'm going to factor the numerator, which this does factor. Factors into 4y to the 8th plus 1 squared. And so now I have something that is a perfect square, and I can plug into the square root in the formula to simplify it pretty nicely. Okay, so there's a formula we're dealing with. And so I plug in our result into the root there, and now the square and the square root will cancel on top, and I can square root the 16y to the 8th on the bottom as well. Notice the interval they gave me was 2 to 4, and so those are my limits of integration on here. And so, okay, so I square root it, simplify that, and so much better now that I don't have to deal with the square root. But I still have this rational expression. So the nice thing is when you only have one term on the bottom, you can always split this up into two separate fractions. So that's exactly what I'm going to do. I'm going to take 4y to the 8th over 4y to the 4th plus 1 over 4y to the 4th. And so that first one's going to simplify to just y to the 4th when I divide those two. And then I get the 1/4. And I'm writing it with a negative exponent because it's easier for me in the next step to integrate that using power rule. So that 1 over 4y to the 4th can be rewritten as 1/4 y to the negative 4. Just don't be careful not to move the 4 to the numerator. It stays at the bottom. Okay, so I can go ahead and do power rule now. So I just did the derivative a few minutes ago, and now I got to do the integral. So I'm adding 1 and dividing by the new derivative or new exponent this time. So 1/5 y to the 5th minus 1 over 12y cubed, which should look kind of familiar from the beginning, which is a common pattern for this type of equation. Okay, so all that's left to do is evaluate this at the limits of integration. So we always start with the top number, plug in 4, and then plug in 2 and subtract. So it looks like something like this when I plug in the values, and remember to subtract. And then it's plugging it into your calculator. If you keep it as a fraction, you get this nice number here. You can also, though, simplify that to a decimal if they're not asking for an exact value. So this is the length of the curve for this particular curve on the interval from 2 to 4. Next thing we want to look at is surface area. So we're going back to those volumes of revolution from the last unit where I take a curve and revolve it around an axis of revolution, and I get this three-dimensional figure. In the last unit, we were finding the volume of that figure. Now I want to actually find the area of the surface. So if I was going to wrap it up in wrapping paper, how much area or how much wrapping paper would I need is kind of the idea here. And we tend to put this with curve length because it's a very similar formula. You'll notice I still have the root of 1 plus the derivative squared. What's different is the stuff out front. So it's important not to forget this when you switch to a surface area problem. You're going to have to multiply by 2 pi and by the original function. The nice thing about this is u substitutions tend to work out more often here because we have this function out front as opposed to with the arc length. Okay, so let's give this formula a try. So we want to find the area of the surface generated when y equals the square root of 4x plus 6 is revolved around the x-axis. I'm revolving around the x-axis. The equation is in terms of x. I should be integrating this one with respect to x this time. And we're on the interval from 0 to 5, so there's our limits of integration. So just like before, I've got to start out with the derivative. So here, that square root can be thought of as a 1/2 power. And so I bring the 1/2 out front, reduce by 1. And then I also have to do chain rule because I've got this binomial in here. So the derivative of 4x plus 6 gives me this 4 here. And so if I clean that up, simplify it a little bit, 4 times 1/2 is going to give me a 2 on the top over that square root of 4x plus 6. This time I'm going to do things a little differently. I'm just going to plug it straight into the formula. Feel free to simplify it some more before doing this, though. But this is what it looks like if I just plug everything in. So the 2 pi is a constant, so I can just pull it out in front of the integral. I've got my limits of integration from 0 to 5. And then following the formula, there's the function out front, and then 1 plus the derivative squared inside of the square root. So I'm going to simplify inside of the square root to start. And I'm doing much like before. I squared the fraction, so the square root is gone. The 2 becomes a 4 in that last fraction there. And then I'm going to rewrite 1 with a common denominator so I can combine these into a single fraction. I'm just trying to simplify this as much as possible before I try to integrate anything. Okay, so if I add those 2 fractions together, the 6 and the 4 combine, so I get 4x plus 10 on the top over 4x plus 6. And so if you're wondering, well, how did I go from this nasty thing to just a square root of 4x plus 10? Well, notice that I have a square root of 4x plus 6 out front, and it's multiplying by this square root of 4x plus 6 in the denominator. So those, because they're multiplying and they're both in square roots, they actually cancel with each other. And I just end up with the 4x plus 10 on the top. So simplified pretty nicely. And now looking at what is left, this is something I'm going to be able to do a u substitution on. So that's where we're going to go from here. Okay, so if I let u be the inside of the square root, so u would be 4x plus 10, then du would be 4 dx, or if I divide the 4 over, since there isn't a 4 in the problem, 1/4 du will replace dx. So I'm going to add in a 1/4 when I swap out the du and the dx, and then I'm going to have the square root of u, or u to the 1/2 inside. Okay, so simplifying the 1/4 times 2 pi gives me pi over 2 out front. And now I can integrate using power rule. So add 1 to the 1/2 and divide by the 3/2 that I get there, or multiply by 2/3. And next I can reverse the u substitution. So plug in the 4x plus 10 again. And don't forget about the 3/2. This is very common. I see students accidentally drop off that 3/2 power whenever they end up with 1 here. And I took the 2/3 and pulled it out and multiplied by the pi over 2, and that simplified to pi over 3. And now I am ready to evaluate at the limits of integration. So plug in the 5 and plug in the 0. And plugging in 0, so plugging in 5 will give me 20 plus 10 gives me a 30 to the 3/2. And plugging in 0 gives me just 10 to the 3/2. And then I subtract. I can't really simplify it much more than this. I've got a few different versions for you to look at here. For instance, I can break up the 3/2 and it would simplify it to look like this. So that's one way you might see the answer. Or if you really want to go crazy, you can even factor some more out of this and it would simplify like this. But really the first version we had right here is fine. You don't have to keep simplifying this from here, especially in a test situation. I wouldn't spend time on it. It also opens you up to making mistakes and getting the wrong answer if you keep messing with it. So this right here is perfectly fine to leave it, or plug it into your calculator if it's okay to give an approximation. So there is the surface area of this 3-dimensional volume of revolution. Okay, so we've looked at curve length and surface area, and here is a couple of more examples for you to try on your own to get more comfortable with these formulas.